And this is in the book, I think, section 5.3, perhaps. And this is an example of a divide and conquer kind of algorithm, very similar to merge sort, but with some little twists that are kind of interesting. And I started out with an example last time of the following permutation: 2, 4, 1, 3, 5. And if you remember, what's an inversion? An inversion is a pair of numbers that are out of order. So 4 is bigger than 1, so that's out of order, because 4 is bigger than 1, yet it comes before 1 in this particular permutation. And 4 is bigger than 3, and yet it comes before 3, so that's an inversion. And also 2 and 1 is an inversion, because 2 is bigger than 1, and yet 2 is there before 1. So this list, or permutation, has 3 inversions in it. And our problem is to count the inversions, count the number of inversions. Okay, well, what we really mean is come up with an algorithm that counts the number of inversions. And the primitive operation in the algorithm is going to be comparing two numbers, just as in merge sort. So we could, a simple algorithm, the simplest kind of algorithm is just to look at each pair of numbers and see whether they're out of order. And if we did that, sort of the naive algorithm would be n squared time, theta of n squared time, because there are n choose 2 pairs, roughly n squared, theta of n squared, pairs. And if you looked at each pair explicitly, then just to see if it's out of order, then your running time is theta of n squared. Okay, so that's sort of the obvious direct approach. And I left you last time with the following question. And we observed that, in fact, you can have lists that have theta of n squared inversions in them. Just taking, for example, 5, 4, 3, 2, 1. Every pair is out of order. Okay, so you certainly can have lists where you can have theta of n squared inversions. And so the question was, does it seem plausible, does it seem possible that you can have an algorithm that will be significantly faster than theta of n squared time, given that there in fact can be theta of n squared inversions? Okay. Remember, we only want to count the number of inversions. So I think somebody at the end last time said, well, you only want to count, you don't want to actually exhibit all the inversions. You don't want to enumerate, you don't need to enumerate them, you don't need to list them. If you did need to list them, then it would take worst case theta of n squared, because there can be that many things that you wanted to list. You can't, nothing comes for free. If you have to output 25 things, it's going to take you 25 operations at least to output them. If you have to output theta of n squared things, in this case inversions, inverted pairs, then it's going to take you at least that many operations to do it. So enumeration is going to take at least that long. And so we have then an optimal algorithm. We have an algorithm that could enumerate all of them in n squared time. And we have an argument that you would need at least n squared time in worst case. And so you have upper and lower bounds meeting, and your algorithm is optimal. But we only want to count, not actually list the inversions. So anybody have any sense of, are we going to be able to do better than theta of n squared? Yeah.
We basically just look at the first element, which is 2, and basically its position is 1. And basically it's imported with 1. 4 is the position 2, and it should be at position 4, and so on. If all the numbers are in order and we don't skip any numbers, basically this works. We take the index and we put like the index of the position, and we see how much that number is bigger than its index.
Okay, so what you're actually proposing is a specific algorithm, and we'd have to really specify and completely make precise what algorithm you had in mind, and then see whether its running time was n squared or better than n squared, and so on. So you're taking a step towards really answering the question by, in fact, coming up with an algorithm. But I was asking sort of a simpler question of whether it even seems plausible at this point. Now, maybe the only way you can address plausibility is by actually having an algorithm. But so that's sort of the algorithmic or mathematical approach to answering the question. What's the sociological or the psychological approach to this question, to answering this question? Well, I mean, the obvious algorithm was n squared time. It was rather trivial. Just look at all the pairs explicitly. They wouldn't make a section of the book on this problem if that's all you're going to be able to do, right? We wouldn't be talking about it in class as a nice algorithm to illustrate something if we couldn't achieve some better time bound than the obvious, okay? So let's do it. It's going to be an adaptation. So n log n will be possible, is possible. And the way we're going to do this is we're going to adapt merge sort. So we're going to effectively do a sorting of this list by using merge sort, but we're going to make some changes so that along the way we'll be able to count the number of inversions that are implied at various points. And we know that merge sort takes big O of n log n operations, or comparisons. So we'll have to be sure that the additional changes we make don't exceed the number of comparisons that happen in merge sort. So we will have additional things going on, but if we want to make the argument that the number of that the comparisons are still the primitive operations, and the number of comparisons is the same as in merge sort, we have to argue that all the other operations we do are still dominated. The number of them is still dominated by the number of comparisons, that comparisons remain a legitimate primitive operation. Okay, so what is analogous to merge sort, we're now going to call sort and count. Or the book calls it sort and count. And you take in a list L. That's the same as in merge sort, right? What's the first thing you do in merge sort? Is what? You divide, or you should check whether maybe the list is just length 1. But generally, so we'll ignore the sort of degenerate case of checking whether the list is already so small we don't have to worry about it. Otherwise, we divide. You divide it into 2 lists of roughly the same size. Now, in merge sort, we said you could do it arbitrarily. It's going to turn out important in this application that the way we do the division is we're going to take the first n over 2 elements, or n is the length of L. The first n over 2 elements as one sublist, and the last n over 2 elements as another sublist. Because in this problem, the left to right orientation of the list has some importance in terms of whether we see an inversion or not. So we'll want to divide the list so we have the left-hand side and the right-hand side. So, and then we also want to we don't need to give it a different name, but the book does. A is the left sublist of n over 2 elements, or integers, and B is the right sublist of n over 2 integers. So this division obviously can be done in constant time because you're just saying, okay, this is my one sublist, the second sublist, okay? And then typically in merge sort, what happens next? You recursively sort A, and you recursively sort B, and then you merge them somehow. So what we're going to do here is we're going to recursively find the number of inverted pairs, count the number of inversions just in A alone. And we're going to recursively count the number of inversions just in B alone. And then we're going to count the number of inversions of one element comes from A and one element comes from B. Okay, and that's all there is. Every inversion in the whole list L is either strictly inside of A or strictly inside of B, or it has one element in A and one element in B. And there are no other possible kinds of inversions. So RA is the number of inversions in A alone. So this is what's being returned from sort and count, which I'll abbreviate that way. So you recursively figure out how many inversions are in A alone by recursively call sort and count on A. Recursively figure out how many inversions there are in B alone by doing a recursive call to sort and count on B. And then you have to figure out how many there are in AB. So you're going to call another procedure called merge and count AB. So this is analogous to the merge sort on A, this is analogous to the merge sort on B, and this is analogous to the merge of A and B. So we have the same basic structure as merge sort. Okay? But what we want is to know how many inversions there are in A alone, how many inversions there are in B alone, and how many inversions are there that cross from A to B. So this is what I want to focus on, because this is just the same superstructure as merge sort, so there's really no additional thinking that goes on there. And when we do merge and count, we're going to actually be merging A and B together. So the merge count AB will return the number of inversions there are that cross from A to B, and it'll also return a sorted list, L. L is going to be sorted now, which is the sorted list of A and B. Well, how do you get the sorted list L from a sorted list A and a sorted list B? Looks like you have an answer. How do you get a sorted list L, which is A of A union B, from a sorted list of A and a sorted list of B? You just merge them the way they do in merge sort. Okay? So the merge and count is going to do merging the same way merge does in merge sort, but we're also going to need to count. Okay? So how does merge work? Pictorially, here's list A, and pictorially, here's list B. Okay? And A is sorted. And B is sorted, right? And let's say this is the small end. These are the small elements, and these are the large elements. So what merge does is it compares the top or first two elements. Whichever is the smaller of those two, it outputs that and removes that element. Okay? I'm not going to write all this down because this is just completely a review of what merge sort does. It looks at the top two elements. Whichever is the smaller of those two, it outputs it and removes it. And then we just go on the same. Okay? So the merging part of merge and count is exactly as in merge sort. Nothing new. It's the counting part that matters. Okay, so let's just look at a little example. Suppose the first one here is 3, and the first one here is 5. Now remember, the elements in A come from the left part of the list, and the elements in B come from the right part of the list. Okay? So does this exhibit, and now 3 is at the front of A, which means it's the smallest element that was in A. But originally, where was it? All we know about where it was originally is if we look at L, where was 3 in this picture? On the left half. It's somewhere in here. Okay? And whereas 5 is somewhere in here. We don't know exactly where they were, but we do know that 3 was somewhere here and 5 was somewhere there. Okay? So is 3 and 5 in the original list an inversion or not? It's not an inversion. It doesn't matter where 3 was here. It doesn't matter where 5 was there. This is not an inversion. Okay? If you ever see when the element you're comparing between A and B, where A is the smallest one, then that's not an inversion. Okay, I'm going to write this part down in a minute, but let's, just to grease up your intuition, let's look at the opposite case. Suppose you had 5 here and 3 there. So now you know that 5 was somewhere on the left side and 3 was somewhere on the right side. And it doesn't matter where 5 was inside here or where 3 was inside there, that's definitely an inversion, right? So when we see that when we're doing a comparison between an element in A and an element in B, and we see that the element in A is bigger than the element in B, that's definitely an inversion, okay? Now the question is, are there any other inversions that you can infer at this point? Yeah.
Four in B right after 3.
You say what? Say that again?
B number 4
Okay.
in list B, but now it kind of 2 inversions.
Yes, it is possible that there could be some additional inversions involving 5 and some other numbers that you're not seeing in B, but I don't know how to get my hands on them without looking at them. 4 might be here, but maybe 6 is here. And so the next one might be an inversion or it might not be an inversion. But what I want is, there's some inversions, I claim there's some inversions that you can know for sure. Yeah?
Well, since 5 is the smallest element in the sort of list A, then all elements in that list are larger.
Right. Since 5 is the smallest element in A, because A is sorted at this moment. Remember, this is inside the merge, sort, and count algorithm. So when we're doing this merging part, A and B are already sorted. 5 is the smallest element in here, okay? And 5 is bigger than 3. So each of the other elements, the ones that are out here, like 26 or whatever it happens to be, that's definitely also going to be bigger than 3, okay? And everybody in A is to the left of everybody in B, so that's definitely going to be an inversion. So what I'm saying is that when you do a comparison between an element in A and an element in B, and you see that the element in A is bigger than the element in B that you're comparing with, what you know is that everybody else who's remaining in A is also bigger. So you can add that to your count even though you haven't looked at that pair explicitly. Okay? But you know already that you're going to have that many additional inversions. Okay, so let me write this down. When you're doing your comparison, so this is in merge count of A and B, and so A is sorted at this moment because we've already had a recursive call that sorted it, and we've had a recursive call that sorted B. In the merge count of A and B, well, first of all, while both lists are non-empty, okay, compare the top element, call it A, of A, to the top element B of B, and then writing down what we just saw by example, if A is bigger than B, okay, it's this case. If the element we're looking at in A is bigger than B, then count, I should have initialized count. Okay. Count equals count plus the size of A. And by size of A, I don't mean the original size of A, I mean the size of A at that moment. Because elements, as we're doing this comparison, you're outputting elements, you're removing elements. If A is bigger than B, then count of A is equal to count plus the size of A, and then we remove A and output it. Okay? But if A is less than B, and that was back to here, it was like this was 3 and this was 5, okay? Then we argued we can't know for sure that there are any additional inversions that involve this number. Okay, so what were we counting here? What we were adding to the count were inversions that involve this number. That was back when it looked like this, 5, 3. We knew that 5 was bigger than 3, and we knew that each one in here was bigger than 5, so each one in here was bigger than 3. So these were all inversions that involved this element. But when you see the opposite case, 3 and 5, well, this is not an inversion that involves this element, and neither can you know yet that any of these will be inversions that involve 5. You just don't know, and so you certainly can't report it at that moment. It might be an inversion. Well, here's 26 is bigger than 5, so there's. But when you're just looking at those two numbers, you can't deduce or infer that any of these are inverted with 5. You have to wait. Okay. All right. So if A is less than B, then what do? We just remove. Wait a minute. Why didn't somebody stop me here? When A is bigger than B, what do we output? B. We should have output B. Or remove B and output it. Okay. When A is less than B, then we remove A and output it. Okay? So this is just the part of what happens in merge. This is the new part. This is saying that when you see that A is bigger than B, then you can deduce a certain number of inversions, and then you add those to the count. And when you're finally finished, you return the sorted A union B. Those are now sorted. That's what you were outputting. And you return count. Okay? So in this sort and count, you've recursively found how many inversions there are in A alone. You've recursively found how many there are in B alone. You have recursively you have called merge and count on A and B, and you return the sorted list A union B and the count R. That's how many inversions there are you've discovered that cross from A to B. And so what do you do at the end? Now we're back to sort and count. In sort and count, how does sort and count end? We have to return something. It's a recursive program. It has to return something. What does it return?
RA plus RB and R.
Say that again?
Like RA plus RB and R.
Yeah, right. You have to return the total count, return R plus RA plus RB. And you also want to return, to go to the, when you're popping back up to the recursive stack, you have to return the sorted list L. Okay, so that's the whole deal on that algorithm. Now, two basic questions we always have. Is it correct? And what's its worst case running time? Okay, what is the worst case running time if we're counting number of comparisons? We're counting individual, when we compare individual integers, that's our primitive operation. So what's the worst case running time for this algorithm? There's a hint here somewhere. Okay. What's the worst case running time of this algorithm? Right, n log n. Who said that? Nobody said that. Come on, guys, wake up. Okay, n log n, but why? Why is it n log n? Yeah.
Except for when you're adding to the count, it's pretty much the exact same operations as merge sort.
Okay. Well, you're arguing that comparisons really are a primitive operation because you're observing that what else are you doing besides comparing? Well, you were splitting the list, but that's only one per recursive call. Here, you're adding a count, but it's an addition that's happening every time you're doing a comparison at most. Some comparisons don't even lead to an addition. So the number of additions here certainly is bounded by the number of comparisons. And so compare remains an appropriate primitive operation. That's good. That's necessary in terms of getting to the final observation here. And then why is n log n the upper bound? Because if you look at the comparisons that are happening in this algorithm, it's just exactly the same comparisons that are happening in merge sort. Merge sort is doing exactly the same operations in merge, and we already analyzed merge sort to show that the number of operations in merge sort was bounded by big O of n log n. So the number of operations here is still n log n, big O of n log n, despite the fact that we're also doing some additional additions. The number of additions are bounded by the number of comparisons. Okay, now why is it correct? First of all, to analyze correctness, the way I think about it, the way I want to do it, there are three things involved. One is that every time you added something to count, it really represented some inversions that we were able to infer or deduce. Okay, and we've effectively argued that. We argued that in our little pictures with examples, that when we see this case, when A is bigger than B, we did infer that there were this many inversions, and they involved elements from capital A with little b. Okay? Those were the pairs that were being counted. They weren't being explicitly enumerated. We weren't listing them, but we have a handle on how many there are of those type, and so we can count them. So that's a good thing in terms of knowing that this algorithm is correct, that whenever it actually adds something into its running count, it actually represents inversions that are in there. But is that the end of correctness? What else do we want to be sure of when we that this algorithm is actually correct? Yeah. Right, that we haven't missed any. So this is saying, yes, whenever we count, there actually are inversions that are associated with that additional addition, but we want to argue that we didn't miss any, that there aren't some that this algorithm doesn't detect. Okay? And what else do we need to check? Termination? I hear a voice, but I don't see a...
Deterministic.
Oh, it's deterministic? Okay. Yeah, okay. Well, formally, we should check that it's deterministic. That wasn't of concern to me because it's fairly clear there's no randomized elements in here. What else do we want to know in terms of correctness? So this is arguing that when you do your addition, there really are that many elements that are inverted. And we'll have to also argue, or we should argue, that we don't miss any. There are no inversions that this algorithm doesn't detect. What's the third possibility? What else? There's a third way that things could go wrong. Yeah?
List L isn't sorted properly.
If list L is what?
Is not sorted properly.
Okay, the sorting of list L we can assume is correct because the structure of the sorting portion here is the same as in merge sort, and we've already proved that merge sort is correct. So, yeah, we can... that part wasn't concerning me. But you're right, that formally, that needs to be in a proof of correctness too. But that part is pretty much handled by our earlier analysis of merge sort. Yeah?
The algorithm finishes and it doesn't count twice an element?
Yeah, it doesn't count twice. Okay, so we wanted to argue that every time it counts, there really are some inversions that it has detected. And we want to argue that there aren't any that it misses. But we also have to argue that it doesn't double count anything or triple count. It doesn't overcount. There's no inversion that's only counted once. There's no inversion that's counted more than once. Each inversion is only counted once. Okay? So that's particularly easy. Well, I said that, let me get this drawing back. So we were looking at the top of A, which may be down here at some moment, and the top of B, which may be way down there at this moment. And we were saying that when we find that A is bigger than B, then we've argued that every other element in A here is bigger than B. And so we're outputting the size of A, the current size of A, as the number of additional inversions that we're counting. Well, each one of those inversions is associated with a pair, AB pair that involves this element in B. So every one of those inversions that we're counting can be charged. That's the sort of the computer science jargon. Can be charged to B, to this little b, bj. Okay? And after that moment in the algorithm, this is removed. Okay? So no additional inversions will ever be charged to this element bj, and therefore every inversion that the algorithm counts is being charged, I was about to say to a distinct bj, but all the ones in this iteration are being charged to there, and so there's certainly no duplicates of that one because they have a different a. And in any additional iterations, successive iterations after this point, no inversions are going to be charged to this guy because he's gone. Okay? So that part of the algorithm is taken care of. Now we still need to argue that no inversions are being missed. Okay? All right, well, on the class website, I actually have a full proof of the correctness of this algorithm. I'll let you read it and understand it, and that way I can ask questions about it and see if you've been able to do it yourself, understand it yourself. I think the proof in the book, or what's implicitly the proof, the discussion in the book that supports correctness of this algorithm is really deficient. I really think you need, it would be good to have a formal, broken down proof that says every time you add an A, you add this many elements, it's because there's certain inverted pairs that you can point to, that nothing is ever omitted and nothing is double counted. And that's what I have on the class website. You can look it up and read it. And you can look in the book's discussion and really see that they don't do it in that rigorous way. But I wanted to point that out as an example of what you really need for correctness. So, in summary, we have an algorithm that was a nice modification of merge sort, n log n comparisons. The algorithm finds the number of inversions that you have in this in any permutation in n log n comparisons. Okay, this algorithm actually, in addition to being a nice illustration of another divide and conquer algorithm, is actually useful. Knowing the number of inversions actually comes up as an interesting operation, and somewhere later in the class, I think I'll show you an example of that that comes from biology. Okay, so I want to show you one last divide and conquer kind of algorithm, a very surprising kind of result, perhaps. One of many surprising results that comes from divide and conquer that involves arithmetic. Arithmetic or matrix multiplication or things of that sort. So this one is integer multiplication. So what do I mean by integer multiplication? 12 times 23. Okay, now I didn't practice this at home. This is going to be embarrassing if I get this wrong. All right, so how do we all multiply two integer numbers together? We use basically an algorithm that you learned in grade school, whether they didn't tell you it was an algorithm. But you multiply 3 times 12. So this is 3 times 12. And then you add together what times 12? 2 times 12? 20, right. 20 times 12. Okay? And why is it 20? Because here we have 2 in the tens position, so this is 2 times 10, so that's 20 times 12. So really, when you're doing your classical multiplication, 3 here, 3 there, and then 2, you're putting the result starting in this position. That really has the effect of multiplying by 20 instead of multiplying by 2. There's a 4, there's a 2, okay? So this was 3 times 12. This is 20 times 12 is 240. Okay? And then you add those together, and you get 6, 7, 276. Okay? So there's really a factoring kind of thing happening here, where you're breaking apart this number into the ones. I guess this is the ones place, the tens place, the hundreds place, and so on. And if I had this 6, 7, well, you get the idea. Be 3 times 20 times 612 plus 700 times 612, like that. All right, so now if you have two, so if we're given two n-digit numbers, how many scalar mult, that means multiplication of individual digits, are done in this sort of grade school way of doing things? Yeah, in terms of n, it is theta of n squared. Okay, digit multiplications, one-digit mults. Okay, so each number is n digits long. So each digit here is multiplied by each digit there, and so we see there's n times n, or n squared, and it's exactly n squared. I mean, we get theta, not just big O. Okay, so theta of n squared, one-digit multiplications. Can we do better? Okay. Well, you can think about that mathematically or algorithmically and see if you can come up with a method that does better. But we probably wouldn't be discussing it in class if the answer was no. So I'm going to show you an algorithm that does significantly better than n squared. By the way, what's better than n squared? N log n is a function that's better than n squared. Order n is a function that's better than n squared. What about square root of n? It's better than n squared. Okay, what about n to the 1.59, just to pick a random sort of, okay. How does that relate to n squared? Well, it's definitely smaller. Yeah, that's good. Good first step. And it's definitely smaller than n squared. And so we can certainly say that n to the 1.59 is big O of n squared. That's true. We never really introduced the right notation to say that one function really is beaten by another function. Okay, so let me just the limit of f of n over g of n is equal to 0. Okay, so if n goes to infinity, so what this is saying is that g really grows faster than f. Okay, because this goes to 0. Then we want to say f of n is little o of g of n. Not big O, but little o. Okay? And so now our question is the following. Is n to the 1.59 little o of n squared? Well, take the ratio, take the limit, and figure it out. And the answer is yes. This is really smaller than that. N squared really grows faster than n to the 1.59. And the difference really becomes significant as n gets bigger. Okay, so we're going to try to achieve the number of one-digit multiplications should grow at this rate, not at that rate. Okay? And at first, I think when people suggested this kinds of results, there were at least some people who reacted by saying, wait a minute, multiplication of numbers is defined by this algorithm, this grade school algorithm that we all learned. That's sort of what is the rock bottom definition of multiplying two n-digit numbers. So how can you possibly do better than this many one-digit multiplications, because that's just somehow implicit in the definition of the result? Well, but if you take a more abstract mathematical view and just say, as long as you get the same result out, whatever this happened to be now, as long as you get the same answer out here, whatever function, whatever computation you're doing that gives you that, which is the same as what this little algorithm would give you, that is a correct algorithm. And in that correct algorithm, maybe the number of one-digit multiplications is smaller, grows smaller than n squared. So that's what we want to do. Now we're going to do that just for illustration. Instead of working in base 10, we're going to work in base 3. No, base 8 or base 2 are natural. We're going to do base 2. Okay, so here's our abstract problem, x times y, and this is going to be these are going to be numbers in base 2. So binary numbers. And x, you can think of x as x1 times 2 to the n over 2. And these are n-bit numbers. Okay? Plus x0. So x1 is an n over 2 bit number, and x0 is also an n over 2 bit number. So I mean, this is just the analogous thing to saying that this was the ones place, the tens place, the hundreds place. Now we have binary places. We have the 1 place, the 4 place, 1 place, 2 place, 4 place, 8 place, and so on. So anybody want an example of this? Okay, I'll give you an example. X equals 1101, that's base 2, is equal to 13 base 10, right? And so what this is saying is that we can think of x is equal to x1, which is 1, times 2, well, n here is 4, so 2 squared, plus x0, which is 0, 1. Okay, now this is really, what kind of object is this? Well, I'm mixing base 2 with base 10. Okay, but I hope everybody forgives me for that. So this is actually binary 1, 1. What's binary 1, 1 in base 10? 2? 3. This is base 10. That's 4. And what's this? It's 1. So this is 3 times 4, which is 12, plus 1, which is 13 base 10. Okay, so if I wanted to be completely rigorous here, I guess I should have written this 2 in base 2, which would have been like that. That's base 2. Here we're squaring it. But here I wrote it in base 10, because 2 is not in base 2, right? Okay. So this was just an example of, you can take any number in base 2 and think of the n over 2 most significant digits times 2 to the n over 2 plus the n over 2 least significant digits, and you can think of it that way. And of course, y1, you can do the same with y1. So I guess I should stop here. We didn't get very far into the method. We'll do this next time. And